Hi guys, welcome to today's video where we will be treating work, energy and power chapter of grade 12. It should be a very short lesson as I'm just gonna walk you through the basics and we're gonna cover examples and exercises in a different video. Let's get to it. This chapter has 5 subtopics: introduction, work, energy theorem, conservation of energy, and lastly power. Introduction. We use the term work almost every day in our lives. Parents going to work, you doing your homework, working in a classroom, etc. But physicists mean something extremely specific when they say work. It is a process by which an object or system transfers energy to another object or system, or one form of energy is being converted into a different form. Hence, in order for work to be done, energy has to be transferred from one system or object to the next object or system. In the second case, energy has to be converted from one form to the next form. For example, when the brakes are applied to a moving car, friction transfers the kinetic energy into thermal energy in the brake pads and discs. One system transfers energy into the next. This is the first case. And the second case, when an electric ion gets hot, it converts the electrical energy into thermal energy. One form of energy is being converted into another form of energy. First, it was electrical energy, and then after it was processed by the ion, it was thermal energy. That's simple. Now, moving on to work. Work is done in an object when a force is applied to it, causing it to slow down or move through a distance in the direction of the force. And force is given by W is equal to F change in X cos of theta. This means that in order for work to be done, an object must have its initial position changed by magnitude of change in X, which is the displacement, while a force F acts on it. The object should either accelerate or decelerate depending on the direction of the force relative to the motion of the object. W represents work, as I've said before, and is measured in joules. And F represents the force in newtons, as I've also mentioned previously, and change in X represents the displacement, which is measured in meters. And finally, theta is the angle between the force and the displacement. Let's take a look at some cases at which work can be, or forces can be applied, or work can be done on objects. The first case is when no work is being done on the object. This is when the force applied is perpendicular to the displacement. The angle becomes 90 degrees, and we all know that the cos of 90 degrees is 0, and hence the whole work formula becomes 0. The second case is when negative work is being done on the object. This is where the component of F is along the direction of the displacement, but in opposite direction. This is when theta is in between 180 degrees and 270 degrees, and theta is greater than 90 degrees. And the last case is when positive work is being done. Now, this is where the component of F is along the direction of the displacement and in the same direction as the displacement. This is where theta is less than 90 degrees, as you can see in my diagram. A truck is traveling along a straight horizontal road. A force of 900 Newton is then applied on the truck, causing it to speed up. During this force, the truck travels a distance of 35 meters. Calculate the work done on the truck. Let's take a look at the solutions. First, let's write down everything we were given. We were given a force that equals 900 newtons, a displacement that equals 35 meters, and theta that is 0 degrees because it's a straight horizontal road. And we know that formula, we just been introduced to it. W is equal to F change in X cos of theta. Substituting in everything, we get W is equal to 900 multiplied by 35 multiplied by cos of 0. That will give me 31,500 joules, or 31.5 kilojoules. And that is how you solve that particular problem. Now let's take a look at work energy theorem. To understand the work energy theorem better, you must first be able to distinguish between conservative forces and non-conservative forces. Conservative force is a force where the work done in moving an object between 2 points is independent of the path taken. The examples are gravitational force and spring forces, and many other. And a non-conservative force is a force where the work done in moving an object between 2 points is dependent of the path. for example, friction, applied force, and many other. Hence, when only conservative forces are doing work on an object, energy changes form from one form to another, potential to kinetic or vice versa, but the total mechanical energy remains the same, or we say it's conserved. Work energy theorem states that the net work done in an object is equal to the change in kinetic energy of the object, represented by the formula in orange I've shown you below. Let's understand the work energy theorem better through an exercise. Let's say a rock of 1 kilogram mass is falling vertically downwards from top of the mountain, 10 meters above the ground, and it hits the ground. Neglect the effects of air friction. Calculate the work done on the rock from the moment it starts falling up until it hits the ground. At first, we know that initially the kinetic energy was 0 because the rock had not started moving yet. And finally, the potential energy was 0 because the rock was on the ground and hence the height was 0. Let's calculate the initial potential energy, which is given by the formula mgh as you've learned in grade 10, substituting in everything I know. I know that mass is 1, gravity is 9.8, and height is 10, and hence the potential energy will be 98 joules. This potential energy is before the rock started falling. But we know that because gravity is a conservative force, it will transfer this energy into another form of energy. Because the rock started moving and a moving object has kinetic energy, this potential energy will be converted into kinetic energy. And hence, final kinetic energy of the rock will be 98 joules. All the potential energy will now be converted into kinetic energy, and the potential energy will be 0. And hence in our formula, we'll substitute in everything I've just said, and we'll have 98, which is the final kinetic energy, minus 0, which is the initial kinetic energy, and hence the net work done is equals to 98 joules. Just like that, you're done. Pretty simple, pretty straightforward. Let's move on to conservation of energy. For conservative forces, work done by conservative forces results in change in potential energy. It can either be stored or released, depending on whether the work is positive or negative. If conservative forces does positive work, then the change in potential energy is negative. Hence, our work done by conservative is given by the formula I've just shown you. Let's relate this to our previous example. In our previous example, a rock was falling from top of the mountain to the bottom. At the top of the mountain, the rock had no kinetic energy because it was stationary, and it had its maximum potential energy. But when it started moving down the mountain, that potential energy started being converted into potential energy up until it was depleted and the rock hit the ground where it had 0 potential energy. One form of energy was converted into a different form of energy, potential energy to kinetic energy. That's what conservative forces do. But now, for non-conservative forces, the work energy theorem becomes change in kinetic energy plus change in potential energy. This is the formula that you need to know for non-conservative forces. And pretty much that's all you need to know regarding the non-conservative forces and work energy theorem. The principle of conservation of energy states that total mechanical energy in an isolated system remains constant. A system is isolated when the non-gravity net external force acting on it is 0. And that is all you need to know about conservation of energy. Now we're going to move on to power, which is a very short subsection as well. We know that power is defined as the rate at which work is being done, or the rate at which energy is being transferred to or from a system. And the formula for power is given in orange, as you can see, and the unit to measure power is watt, represented by the symbol of capital letter W. And that brings us to the end of this lesson. Thank you for watching. To support the channel and help more students access free lessons, please like the video and subscribe to the channel. For additional learning materials and updates, visit our website using the link in the description below. Keep studying hard, and I'll see you in the next one. Cheers.